equation, Jaden, right? Which is F equals ma, right? Where M
Right.
is the mass
And isn't
sum.
that like one of Newton's laws or
Yeah, it
something
is
like
one of,
that?
dude, it is one of
Ah,
Newton's laws.
sweet.
Um,
Okay, so force equals mass times acceleration.
right. Where mass is one
Okay,
of the, mass is one of the mass of the object, and then acceleration. Remember, acceleration is how quickly its velocity is changing. Okay.
okay,
So from there, we can go ahead and there's another equation for the force of gravity, which is this. G, or sorry, whoop, F of G equals big G, which is the gravitational constant, times
okay,
mass 1, okay, times
okay,
mass 2, and this is divided by the radius squared. Okay?
okay. Um, and with the minus sign out here, right?
Yeah. Don't forget your signs. Signs are important.
Yeah. And the little g with the force, like the F, right? F of g, that just means the force of gravity in this case, right?
Right. So that's the
Yeah.
force. So sorry, let me back up a little bit. We need to talk really quickly what the force of gravity is, I guess. So the
Okay.
force of gravity, we can see from this equation, is related to two masses, right? Up to this point, we've been dealing with just a single mass. But every
Right.
object is attracted to another object by gravity,
Like
right?
Romans?
Yeah, just like that. I actually have a shirt designed that I'll maybe show later on in tonight that is about that's about the force of gravity, and the punchline goes something like, the closer we get together, the harder I fall for you. It's pretty clever.
That is pretty clever.
Because see that r squared, as that gets smaller, the force of gravity, right? The closer you get to something, the closer two objects get together, the stronger that
Right.
force of gravity is. And so, yeah, so my shirt says, the, anyways, yeah, that says what I said that I'm forgetting now. But, um, so we've got let's keep looking here.
All
Um,
right, we have a couple of questions in the chat.
oh yeah,
Kelsey says, I want to see both of your sweaters and see whose is cooler. That's not much of a question. It's much more of a demand, and we are kind of fresh out of demands. Uh, but Carsey says, why would anyone know any of this? Why would why would someone just know this stuff, Kip?
well, I don't know if many people just know this stuff. I went to school for it. Jaden, you went to school for it. But
Yeah.
on top of that, most of us do experience gravity quite frequently, right? Like if you were to drop a
Uh,
pencil,
you mean every single second you've been alive, you've
yeah,
experienced it?
exactly. It's like that, in this Flat Earth documentary, they're actually talking about why they don't believe the Earth is flat, and one of the reasons why is because we're rotating so fast, right? And well, then why can't we feel it? And part of that's thanks to gravity sticking us to the same spot, and that's why we can't feel it. So, but as far as the
Uh,
mathematical equations go, that's when you need to go to school to have someone teach you, or you can tune into Aftermath and we'll show you. So hit that subscribe button down below. Anyways,
hey, yeah. Okay.
okay.
All right.
Thanks for those questions. If anyone has any other questions, please let them know. By the way, my sweatshirt is better. It has a throwing up unicorn on it. So,
Okay. I'll give you that.
Okay. So let's get back to some aftermath here. Okay.
Yes.
Um. So Jaden, we can do something, right? We can plug in this F.
Right.
Oh gosh, I'm on my eraser. We can plug in this F for that F. So we can get MA is equal to G times M1 times M2. Thank you.
You're welcome.
R squared. Um, so then from there, we can go ahead and um,
And what mass is the first one talking about? It doesn't have a 1 or a 2. So what mass is that representing?
so yeah, so this mass we're gonna say is equal to the mass. We can choose whatever mass we want, right? Because of Newton's laws, there's an equal and opposite reaction to everything, right? So the mass that's acting on
Right.
the force that's acting on mass 1 is the same force that's acting on mass 2. So all that matters is we just need to decide which mass we want to work with. Normally, we'll say mass 1 is, the Earth in this case, and we'll say that mass 2 is our
Okay.
satellite. So we'll say that this is
Okay.
mass 2. Okay?
Okay.
And so from there, we can actually go ahead and we can cancel these two masses out. We do have a questions coming in though, about
Oh yeah.
contrails. Um, I'm not sure if I know the answer to those ones, but
What? uh, why does a contrail approaching you from the horizon look like it's going up, and contrail going away from you on the opposite horizon look like it's going down? Then Kelsey comments, "What is a contrail?" I am on the same boat as Kelsey. I don't know what a contrail is. Uh, and then Carsey says, "Well, that was from Brad, the contrail question."
yeah. So a contrail,
Contrail is a
Jaden,
French
is
word. Okay.
that thing that you see behind the plane, right? When you're
Ah,
the
okay.
chemtrails actually, Brad has it wrong. It's actually a chemtrail. They're dumping chemicals, and that's why we see what we see. As far as Carsey's question about what's the difference between mass and weight, um, if Carsey would have been here on one of our earlier videos, we would have had the answer to that already, but that's all right. We got new subscribers, so we'll go ahead and answer that this time. So for
Yeah.
Carsey, mass is how much of something exists, right? It's the total amount of stuff, whereas weight is the force, or yeah, it's gravity acting on that mass. So for example, when you're on Mars, wow, dude, I just got attacked by something. When we're on Mar when you're on Mars, your weight is different than your weight on Earth because of
That.
that, but your mass stays the same.
Yeah. Hope that answers your question.
Yeah. Um,
Okay.
so I got an email question, which is actually exactly what we're working on, which is how does a satellite work? So that's pretty good. Um,
Okay. Awesome.
we'll come back to the contrails question later. I'm not quite sure exactly what they're asking.
I think that just has to do with the curvature of the Earth,
Yeah.
and how if you're looking into the horizon, it might look like it's coming up at you, and it could also look like it's going down, like the same situation. I don't know, just different perspectives. I don't
That's
know.
good. I don't have the math for that. Sorry, Brad. We'll have to come back to that one later. So, back to our orbits question, right? So, we now have this equation, which is the acceleration of the object is equal to the
And
gravitation. What?
so, Kip, when you just crossed out M2 on both sides of the equal sign, what exactly happened there? Just to
Dude, do you want me to, do
clarify.
you want me to tell you what happened, dude? It was
Yeah.
it was math magical. Um, but but the
Wave
how
the hand.
yeah, dude, just wave the hand. It's actually, I mean, it's something that I know from intuition. If you have something that's, being multiplied on both sides, you can cross them out. But the reason for that is if we're trying to get acceleration by itself, we can divide
Right.
this m2 on both
So we're
sides.
using inverse operations
Right.
to divide M2 on both sides. Okay, and then it just cancels each other out. Anything divided by itself equals 1, and
Right.
1 times anything doesn't change the problem. Okay, cool.
Cool. Darcy responded, by the way, saying the answer to the on-trail question is because the Earth is round. So, Jaden, you are correct.
Sweet.
Okay.
Okay, so we have our equation here. Acceleration equals big G times m1. All of that is divided by r squared.
Right. So,
Okay.
Jaden, do you notice anything interesting about this equation that might stand out to you that, I don't know, is significant?
Well, the big G and the M1, those are constant, right? Because one is the gravitational constant and M is the mass of the Earth, which, as far as I know, isn't changing all that much, and that's what I've noticed. What about you?
So, yeah, that's true. And then the other thing that I've noticed on top of that is that our um, our acceleration of our object, thanks for that negative comment again. The acceleration of our object is has nothing to do with its own mass, right? So it actually, the acceleration has nothing to do with how, what the mass of the satellite is. It could be this massive, massive satellite, and it doesn't matter, right? The only thing that
You're
matters,
telling me that this massive, massive, really, really heavy satellite would be affected the exact same as a piece of paper?
that's what I'm telling you.
What the heck? Why is that so hard to believe? But the math shows exactly what we were just saying.
Exactly. It only depends on the mass or, around what the other mass is, right? So if
Okay.
it was the other way around, if we were trying to figure out what the acceleration of, you know,
Of
the
Earth.
acceleration of the Earth compared to the piece of paper, the mass of the Earth wouldn't matter, but the mass of the paper would.
That's
So
crazy.
a little bit of math there for us.
Yeah.
Okay, so let's keep moving forward. The goal of tonight is we want to be able to calculate how fast something's going to have to be going to stay in orbit, depending on the radius at which it's at. Okay,
Okay.
so from there we can go ahead and say that, well, let's think here. What
So
should
we
we do
get a new
next?
page or
Sure, let's get a new page. And
We can.
I will write that equation here again. So A equals G mass 1 over R squared. Okay. So now from here, so for those that need a quick refresher, acceleration is the of the changing of velocity, right? So that doesn't necessarily mean that it's slowing down, right? If we're in two dimensions, it would either have to be slowing down or speeding up, right? You'd have this,
Right.
or maybe not two dimensions. I get one dimension. Sorry, if we're in one dimension, it'd be slowing down or speeding up. But
Right.
because velocity is a vector, it has direction associated with it. So the acceleration isn't just the slowing down or speeding up, but actually the change in direction of velocity as well.
Okay, so you're saying, like our cannonball example, if you want it to orbit the Earth, we have this tangential velocity, which means it's going in one direction, but because of gravity, we see this curvature, and so the tangential velocity will stay the same, but because it's accelerating, the velocity is changing. How is that? How does that make sense?
So its speed is staying the same, right? So when we
Oh,
talk
okay.
about speed, you think of things like miles per hour, right? That's a speed. It doesn't have any direction associated with it. So if we're
Okay.
going 50 miles an hour, that's a speed.
Okay.
Now let's say that we're going 50 miles per hour to the west. This is now a velocity. And the
Because we
reason
have
why we have a
speed
direction,
and direction.
right? So we have
Okay.
that direction associated with it. Um, so the reason why that matters is, let's say that we kept going 50 miles an hour, right? Your speedometer kept saying 50 miles an hour, but now instead of going to the west, you're going south. So you made a 90-degree turn and now you're going south, but you've stayed going 50 miles an hour the whole time. There's actually an acceleration that is happening during that time because you're changing direction. And so the
And
same, yes.
pretty sure everyone felt that acceleration, right? If you are turning and you're still going relatively the same speed, you feel like it feels like a force is pushing you against like the side of the car one way or another. Uh, but it's not actually the force, right? It's just this change in velocity due to the acceleration.
Exactly. Um, so if we come back to our equation here, um, we need to be able to associate our acceleration, but now we're changing our velocity. So we need to um, have our acceleration somehow be related to our velocity. Um, and I am trying to remember this equation. I don't have it memorized off the top of my head right now.
Neither do I.
Um, we're going to get there though.
Trying to get out the heavy duty book. See if that can help us out.
What heavy duty book? I'm pretty sure it's A equals V divided by R squared, but I could be wrong here. Okay. I know I'm missing something. Okay. Acceleration due to the change in the direction is, I had it backwards. It's v squared over r equals a. Okay.
Okay.
So we can go again and plug this in, and we get v squared over r is equal to constant for gravity m1 divided by r squared. And then again, using some mathematical math here, we can cancel out one of these
Ooh,
r's on
okay,
that
I
side
got.
and that side, and we get v squared is equal to g
Yeah.
m1 over r.
Okay. And we could take
Okay,
that one step further, right? Get the
absolutely. What do we do from
velocity
there?
without the squared. Nice.
So to do that, Jaden, what do we want to do?
We want to take the square root on both sides of that equal sign. Doing that will leave us with, there's a square root, there's a square root. Boop. Doing that will leave us with v equals big G m1 over r. All of that under the square root.
Cool, cool. Let's double check that that is the correct answer before we publish this and say that it is.
It is. I
It
have
is.
big book confirmation.
So this question is solved. Okay,
Whew.
dude, we did it right. Look at that. And we only had to look up one equation the whole time.
That was pretty impressive.